Imagine opening your video with a question that immediately grips the audience's imagination. The cosmos is filled with mysteries, but among them, black holes hold a special place in our collective curiosity. They are the monsters of the universe, swallowing stars, bending time, and hiding secrets behind horizons of no return. But what if we told you that black holes might not be alone? That somewhere in the fabric of space-time, their opposites could exist, cosmic siblings that don't devour, but expel, that don't trap, but eject. This is the idea of white holes. To bring your viewers into this dialogue, picture the voices exploring the concept as if they were unraveling a mystery together, each line pulling the listener deeper into the unknown. The first voice, curious and dramatic, might start, "We all know black holes as the universe's vacuum cleaners, right? Once something falls in, it's gone forever. But have you ever heard of their theoretical twins, white holes?" The second voice could respond with surprise, "White holes, what's? That's some kind of science fiction idea." And here's where the first voice smiles through words, not science fiction, science theory. If black holes take everything in, white holes are predicted to spit everything out. This kind of playful banter immediately sets up a strong hook, making the audience lean in. Your narrative should paint white holes as something exotic, almost mythological, yet grounded in physics. Set the stage by contrasting them with black holes. Think of a black hole as the universe's ultimate trap. Now imagine flipping the laws. Instead of pulling matter inward, this object pushes everything outward like a cosmic volcano that can't be approached, only observed from afar. That paradox immediately intrigues anyone listening. After all, it's natural to wonder if black holes exist and we've seen their shadows. Why shouldn't white holes be real too? The key in this opening is drama and curiosity. You don't need to get technical, yet just highlight the contrast. Viewers don't need equations to be amazed. They need a reason to stay, and the white hole gives that reason in spades. You might even tie it to human imagination, from myths of God spitting out stars to modern-day physics. We've always been obsessed with creation and destruction. Black holes destroy, but white holes, they could be the ultimate creators. Another way to deepen the hook is by introducing a sense of rarity. Explain that while black holes have been imaged and studied, white holes remain ghosts of theory. That's what makes them so tantalizing. People love stories about hidden, unexplained things. It's like telling your audience, here's a secret chapter of the universe most people don't even know exists. You're inviting them into a kind of cosmic conspiracy, one that feels thrilling to be part of. You might want to use rhetorical questions to keep the suspense flowing. If black holes exist in the billions, could white holes be lurking somewhere too? And if so, why haven't we seen one yet? Are they too rare, too short-lived? Or could they be hiding in plain sight? By not giving immediate answers, you tease what's to come, making your viewers want to follow along section by section. At this point in the narrative, it's effective to add a touch of drama by reminding the audience how mind-bending the universe can be. People often think science is about certainty, but physics thrives on possibilities. You could phrase it like this: what we know about the cosmos is vast, but what we don't know could fill endless galaxies. White holes sit right at that frontier, where imagination meets mathematics. Where we ask, could the universe have objects that behave in ways we've never seen? This opening works best when it feels like a cinematic reveal. Imagine music swelling in the background, voices rising with excitement as the concept unfolds. One speaker, skeptical but intrigued, plays the role of the audience surrogate, asking the questions viewers themselves might ask. The other speaker takes the role of the guide, explaining, teasing, and revealing the strange possibilities that lie ahead. Above all, the introduction should feel like an invitation into a story. Science isn't just facts, it's a narrative of discovery. Frame white holes as a story we're only beginning to tell. The characters, us, the explorers. The setting, the cosmos, the plot. Finding out if black holes really do have mysterious siblings that reverse the rules of reality. That's how you spark curiosity right from the first seconds. Close this section with a line that leaves the audience on edge, ready for the next part. Something like, so, if black holes are the universe's devourers, white holes could be its givers. But before we dive into these mysterious siblings, let's remind ourselves what makes black holes so terrifying in the first place. This not only caps off the introduction neatly, but also naturally sets up the flow into the next bullet point: black hole basics. Before we can truly appreciate what makes a white hole fascinating, we need to remind ourselves of its dark sibling, the black hole. After all, you can't understand the idea of an opposite unless you first grasp what it's opposing. So, slow down and sink into the strange reality of black holes. Because the more bizarre they sound, the more incredible the white hole will seem. The dialogue here works best if one voice takes the role of an eager explainer, while the other voice plays the skeptic or the student. Imagine the first speaker saying, black holes start life as stars, massive stars, far bigger than our sun. When they burn through all their nuclear fuel, gravity takes over and collapses the star inward. What's left is an object so dense that nothing, not even light, can escape. Immediately, the second voice might jump in. Wait, nothing can escape, not even light. Then how do we know they're even there? That's the perfect point to explain how we detect black holes, not by seeing them directly, but by their effects on nearby stars, gases, and even the bending of light itself. Black holes are more than collapsed stars, they're extreme distortions in the very fabric of space-time. Here, you can dramatize the concept with a metaphor your audience will latch onto. One voice could explain, Imagine space-time as a trampoline. Put a bowling ball on it and the fabric dips. That's how gravity works. Now, replace the bowling ball with something infinitely heavier, a collapsed star with all its mass squeezed into a tiny point. The trampoline doesn't just dip, it rips downward into a funnel that seems bottomless. That's a black hole, and that's where you introduce the famous idea of the event horizon. The explainer might continue. The event horizon is the point of no return. Once you cross it, you're trapped forever. Space itself is being pulled inward faster than light can travel outward, which means escape is impossible. The other speaker might add a dramatic pause, so step too close, and you're gone forever. That tension not only builds drama, but also makes the audience feel the stakes. At this point, you can expand into the mind-bending consequences black holes have on physics. Time dilation is a great hook. The dialogue might go something like this. Speaker 1. What's even crazier is that time itself slows down near a black hole. If you hovered close to one, you'd experience time at a different pace than someone far away. Speaker 2. So, wait, if I had a twin who stayed safely away, and I spent a day near a black hole, when I came back, my twin might be years older. Speaker 1. Exactly. Black holes don't just bend space, they bend time. They're like natural time machines, but only forward. By now, your audience is wrapped up in the awe and terror of black holes. That's when you can describe them. Singularity, the ultimate unknown with a hushed tone. You might explain, at the very core lies the singularity, a point of infinite density. It's where the laws of physics as we know them break down. You can't describe it with our current theories, it's the universe's ultimate mystery. The second voice can punctuate that with disbelief. So, basically, it's a place where physics throws up its hands and says, I give up. That humor softens the tension, but also emphasizes the limit of human knowledge. It's worth noting that black holes aren't rare monsters lurking in the corners of the universe. They're surprisingly common, sprinkled in some facts too. Make it more grounded. Our galaxy, the Milky Way, is home to millions of black holes. And at its very center lies a supermassive one called Sagittarius A*, with a mass 4,000,000 times that of our sun. The second voice could react with awe. Wait, so our entire galaxy orbits around a black hole? That's terrifying and beautiful at the same time. You can also mention the first real picture of a black hole, captured in 2019 by the Event Horizon Telescope, showing that faint glowing ring around darkness. It's proof that these monsters aren't just theoretical, they're real, observable, and shaping the universe around us. This anchors the dialogue and reality, making what comes next, the discussion of white holes, feel even more provocative. By comparison, by now, your viewers understand black holes not just as scary space concepts, but as tangible objects we've studied and confirmed, and that's exactly the setup you want. Because when you flip the script and introduce white holes, the contrast becomes almost mind-blowing. The key is pacing. You want the audience to feel grounded in the science of black holes, so that when you say, now imagine the exact opposite, their minds are ready to be blown. Wrap up this section by giving your audience a transition that teases what's next. A closing line like, so if black holes are the universe's ultimate trap subjects that swallow light, matter, even time, what happens if we imagine their perfect opposites? Welcome to the strange world of white holes. That line not only summarizes the section, but also launches you neatly into the next narrative beat, keeping your audience hooked for the ride. Now, the foundation of black holes is firmly in place. It's time to flip the cosmic coin and look at the other side. If black holes are all about devouring and trapping, then white holes are about spewing and rejecting. They are, in a sense, the theoretical opposites, the cosmic exhalation after the cosmic inhale. To understand them, imagine everything you just learned about black holes turned upside down. In a dialogue format, one voice can lean in with curiosity. So if a black hole is a trap you can't escape, a white hole would be, what, exactly? A fountain that you can't enter. That's a perfect way to describe it. White holes are theorized to push matter and energy outward, refusing to let anything cross their boundary from the outside. If a black hole is a one-way door pulling you in, a white hole is the locked exit door forcing everything out. To make it clear for viewers, you might compare it to everyday experiences. The explainer could say, imagine trying to throw something into a volcano that only explodes outward. No matter what you toss in, it blasts it right back at you. That's the idea of a white hole. There's no way in, only out. The second speaker could respond with amazement. So it's like a black hole in reverse. Nothing can enter, but stuff can still come out. That interplay makes the paradox stick in the listener's mind. The real kicker here is how naturally white holes emerge from mathematics. They aren't inventions of science fiction. They're serious solutions to Einstein's equations of general relativity. In fact, when physicists first worked out the equations describing black holes, they realized those same equations also allowed for the existence of the exact reverse objects that could only expel and never absorb. This is what makes white holes so fascinating. They're not wild guesses, but inevitable byproducts of the very same math that predicted black holes, which we now know exist. That point allows you to add a little drama. Speaker 1 might say, when Einstein's math said black holes could exist, people thought it was nonsense until telescopes proved them real decades later. So, when that same math says white holes could exist, should we dismiss it so easily? The other voice could add, exactly. Just because we haven't seen them doesn't mean they're not out there, hiding somewhere in the universe. Here's another way to spark the audience's imagination. Highlight how alien these objects would look if we could observe a white hole It might appear as a blinding source of radiation and matter suddenly blasting into existence. Imagine a point in space that seems to erupt with energy, but if you tried to approach it, the laws of physics would forbid you from crossing its boundary. This is the exact opposite feeling from the abyss of a black hole, where everything vanishes into darkness. With white holes, you get sudden brilliance and rejection. The second voice could raise a natural objection, but hold on. If they're constantly spewing stuff out, wouldn't we have noticed one by now? Wouldn't they light up the sky? That's where the dialogue gets intriguing. The explainer can respond. That's the mystery. Either they're so rare that we haven't spotted one yet, or maybe they only exist for short bursts of time. Some physicists think mysterious cosmic flashes like gamma ray bursts or fast radio bursts could be white holes revealing themselves for just a moment before vanishing. This speculation not only keeps things exciting, but also teases what's coming later in the script. Another strong angle is to emphasize how white holes would redefine our sense of balance in the universe. One voice might say, it's almost poetic. Black holes suck in matter, hiding it away forever. White holes would be the opposite, throwing matter back into the cosmos. It's like the universe's destroyers and creators, yin and yang. That poetic imagery resonates with viewers, reminding them that science often mirrors ancient ideas of balance and duality. The dialogue can also explore the difficulty of proof. While black holes announce themselves through their gravitational effects on nearby stars and gas, white holes would resist being found, since nothing can cross into them. They wouldn't create the same kind of gravitational feeding frenzy we see with black holes. That makes them even more mysterious. They might exist, yet remain completely hidden from us, except perhaps in rare bursts of energy. Close out the section by leaning into the drama of uncertainty, a good way to phrase. It might be. White holes are one of those cosmic riddles where theory races ahead of evidence. They're the mathematical ghost of black holes, haunting the equations of physics. Are they real? Or just the universe's way of teasing us with possibilities? The second voice could leave the audience with a playful cliffhanger. Well, if Einstein's math is anything to go by, maybe the universe is hiding them in plain sight. But before we go chasing ghosts, let's dig into where these strange ideas actually come from Einstein himself. That sets the stage perfectly for the next section, where the dialogue dives into the roots of white holes and relativity. To truly understand where the idea of white holes comes from, we need to go back to the roots of modern physics, Einstein's theory of general relativity. This theory, published in 1915, describes how matter and energy warp space-time, creating what we feel is gravity. It's the same framework that gave rise to our understanding of black holes. What makes the story fascinating is that Einstein's equations don't just allow for one strange solution, they allow for multiple. And white holes are one of those hidden possibilities. In a dialogue style, the first voice could begin with excitement. So, black holes weren't just dreamt up out of thin air, right? They came straight out of Einstein's math. The second voice might respond, exactly. And here's the kicker. Those same equations also predict the existence of white holes, even if we've never seen one. That's the hook, the idea that white holes are not speculative fiction, but mathematical siblings born from the very same theory that has been tested and confirmed countless times. One of the most important solutions of Einstein's equations is called the Schwarzschild solution, discovered in 1916. It's the simplest mathematical description of a black hole and object with mass but no charge or spin. The fascinating part is that the Schwarzschild solution doesn't just describe a black hole region. Mathematically, it also describes another region that looks like a white hole. In other words, the math naturally creates both halves of this cosmic coin. One part of the solution pulls matter inward, the other pushes it out. This is where the dialogue can lean into imagination. Speaker one might say, so you're telling me the math that gave us black holes, the monsters we now know are real, also tells us that white holes should exist? The explainer can reply, that's right. In fact, in the full mathematical picture, a black hole and a white hole are the sides of the same space-time structure. That structure is sometimes called an Einstein-Rosen bridge, which we'll dive into later. But for now, it's enough to point out that general relativity doesn't shy away from weirdness. It embraces a dot to make this digestible for viewers. You can use time reversal as a metaphor. Black holes are like movies of matter falling inward. White holes are those same movies run backward, matter flying outward. And the beauty is that relativity doesn't forbid this. The equations are symmetric in time. So if you can have one, you can have the other. The second voice can add wonder. That's wild. So physics is basically saying, if destruction exists, creation must exist too. But here's where you can stir intrigue by showing the limits of theory. While relativity predicts white holes, physics is not just about math, it's about observation. And so far, we have zero observational evidence of white holes. That makes them theoretical ghosts, haunting our equations without ever appearing in the sky still. Remember that black holes themselves were once dismissed as purely theoretical. Einstein himself didn't believe they'd ever be observed. It wasn't until decades later that we found indirect evidence. And only in 2019 did we finally capture their image. So, who's to say the same won't eventually happen with white holes? The dialogue can emphasize this with a skeptical exchange. Speaker 1, but if we've never seen one, why even take the idea seriously? Speaker 2, because the same math that once predicted black holes and proved everyone wrong predicts white holes too. History has taught us that ignoring Einstein's equations is a dangerous bet. That argument not only highlights the weight of relativity, but also primes the audience for curiosity rather than dismissal. At this stage, you can sprinkle in a little historical flavor. Point out that the concept of white holes first started to gain attention in the 1960s and 70s, when physicists were studying the full implications of relativity. It was during this era that the connection between black holes, white holes, and wormholes began to emerge. Theorists realized that if you fully extended the Schwarzschild solution, you didn't just get a single black hole, you got an entire space-time map. That included both black holes and white holes, connected by tunnels. This gave rise to the idea that perhaps white holes could be more than just equations. They could have real cosmological roles. This is a great place in the dialogue to use dramatic imagery. The explainer could say, imagine a universe where every black hole, somewhere beyond its event horizon, connects to a white hole, blasting matter into another region of space. It would mean that when something falls into a black hole, it doesn't just vanish, it comes out somewhere else. The skeptic voice could cut it, so like a cosmic recycling system. The guide could reply, exactly. Destruction on one side, creation on the other. It's important, though, to temper this with the acknowledgement that relativity is not the final word. White holes may be mathematically elegant, but the laws of thermodynamics and quantum physics raise serious challenges to their existence. But holding that thought off for now creates suspense. You want to keep the audience intrigued. And you'll get into objections later. The best way to wrap up this section is to underline the key point. White holes are not random fantasies. They are predictions of the same scientific framework that has already reshaped our understanding of the universe. Whether they exist or not is a mystery, but the math is clear. That sets up the perfect transition into the next section, if relativity allows them. Why haven't we seen any? Why is there no direct evidence? So far, white holes sound like cosmic wonders, brilliant, explosive siblings of the black holes we know and fear. But here comes the big problem: they've never been observed. No telescope has ever caught sight of a white hole in action. In fact, everything we know about them comes from math, not evidence. This absence is crucial, because science is built not only on theory, but also on observation. Without observational proof, white holes remain in the realm of speculation. The dialogue can open with a skeptical voice asking the obvious: if these things really exist, why haven't we seen one yet? Black holes reveal themselves through their gravity, their collisions, their shadows. Shouldn't white holes be even easier to spot, since they're spitting out energy and matter? That's exactly the paradox. If white holes existed, you'd expect them to be loud, bright, and messy. Instead, the skies remain quiet. The explainer voice might respond, that's the puzzle. According to relativity, white holes are possible, but when you bring in other physics like thermodynamics, they become unstable. Anything that spews out matter and energy constantly should eventually run into interference from its environment, and if even a tiny particle from outside were to hit a white hole, the math suggests it would destabilize and collapse. In simpler terms, white holes may be so fragile that they couldn't survive in our universe long enough for us to notice them. Here's where you can heighten the intrigue by contrasting them with black holes. Black holes are stable. Once formed, they can last billions upon billions of years. They even grow larger by feeding on surrounding material. White holes, on the other hand, may burn bright and vanish in an instant, unable to withstand the universe pressing back on them. The skeptic might remark, so white holes are like fireworks, spectacular, but gone in seconds. The guide could agree, exactly. And if they last such a short time, it's no wonder we've never managed to spot one. This leads naturally to some of the most fascinating modern theories. Some physicists speculate that mysterious cosmic events like gamma ray bursts or fast radio bursts could actually be white holes revealing themselves briefly. Gamma ray bursts are among the brightest explosions in the universe, releasing more energy in seconds than our sun will emit in its entire lifetime. No one knows exactly what causes them. Could they be the death screams of collapsing stars? Or could some of them be white holes, briefly flaring into existence before fading? That mystery keeps the door open. The dialogue can dramatize this by having the skeptic ask, so when astronomers detect a sudden flash of energy from deep space, are you saying it could be a white hole? The guide might respond cautiously, it's possible. Most bursts are probably from supernovas or neutron star collisions, but a few remain unexplained. And in those gaps of knowledge, white holes could hide. That balance between grounded science and open-ended wonder is what keeps viewers hooked. Another point worth weaving into this section is the philosophical side of scientific evidence. Black holes, remember, were also once purely theoretical. For decades, they were thought to be mathematical oddities with no real-world counterpart. Even Einstein himself doubted they could ever exist in reality. And yet today, we have seen the shadow of a black hole and recorded the ripples in space-time caused by their collisions. That history lesson sets up a powerful rhetorical question. If black holes went from theory to reality, could white holes follow the same path one day? The skeptic voice might ask bluntly, but if we've seen nothing yet, doesn't that suggest they're not real? The explainer can counter, not necessarily. The universe is vast, and we've only observed a fraction of it with our current technology. Some objects are so rare or short-lived that we might only detect them with future instruments. Science has a long history of discovering what once seemed impossible. There's also the possibility that white holes don't exist in our universe at all, but play roles in theoretical extensions of physics. For example, in quantum gravity theories, White holes sometimes appear as necessary counterpoints to black holes, ensuring balance in the equations. That doesn't mean we'll ever see one in the night sky, but it does mean they may have a role to play in understanding reality on the deepest level. The best way to close this section is to lean into that tension between absence and possibility. One voice could say, so far, white holes remain invisible, theoretical ghosts haunting Einstein's equations. But history tells us that the universe is always stranger than we think. Maybe the absence of evidence is just temporary. The other voice could set up the next section with intrigue. And if these ghosts are more than math, maybe they're connected to something even wilder, wormholes. Because what if white holes aren't just out there alone, but tied directly to black holes? That question creates a perfect handoff to the next narrative step, the potential connection between white holes, black holes, and wormholes. If white holes sound strange on their own, things become even more mind-bending when scientists speculate that they might be linked to black holes through wormholes. The idea of a wormhole, also called an Einstein-Rosen bridge, is one of the most captivating in physics. It suggests that space-time might not be flat and continuous, but rather folded in such a way that shortcuts exist between distant points. Black holes and white holes, in this view, could be the cosmic gateways anchoring those tunnels. The dialogue here can capture the excitement of possibility. One voice might say, so wait, you're saying that a black hole on one side and a white hole on the other could form a tunnel through space-time? The guide could answer, exactly. Imagine falling into a black hole, instead of being crushed at the singularity. What if you emerge somewhere else through a white hole? Immediately, the imagination comes alive. It's the stuff of science. Fiction, but rooted in equations. To explain it clearly, think of space-time as a sheet of paper. If you draw the points on opposite ends and fold the paper so they touch, you've made a shortcut. That's the essence of a wormhole. In relativity, when you extend the equations that describe black holes, they naturally create a structure with two openings. One is a black hole, pulling matter in. The other is a white hole, pushing it out. The tunnel connecting them is the wormhole, of course. That sets up the perfect skeptical question. But hold on, if wormholes exist, why haven't we traveled through one yet? Wouldn't that mean instant shortcuts across the universe? The guide can respond with caution. That's where reality bursts the bubble. Wormholes, if they exist, are predicted to be extremely unstable. They would collapse in on themselves faster than anything could pass through, without exotic matter or some form of negative energy. To hold them open, they slam shut instantly. Here's where you can stir excitement by weaving in both science and imagination. The concept of exotic matter material with negative energy density sounds like pure fantasy, but it's something physicists have considered seriously. If such matter could exist, it might prop open a wormhole long enough for something or someone to travel through. The dialogue might lean into the mystery, so if we ever wanted to travel through a wormhole, we need a kind of matter we've never seen. That's right, and if we could find it, the universe might suddenly shrink. Galaxies billions of light years away could be just a step through the right doorway. The connection between black holes, white holes, and wormholes also raises another fascinating idea. Could white holes explain where the matter swallowed by black holes goes? In our current understanding, once matter passes the event horizon of a black hole, it's gone forever, or at least, it's hidden from our universe. But if wormholes are real, maybe that matter isn't lost. Maybe it's ejected out of a white hole somewhere else, possibly in another part of the universe, or even another universe entirely. That's when you can drop one of the most dramatic comparisons. Speaker one might say, so, black holes could be drains and white holes could be faucets, with wormholes as the pipes connecting them. Speaker two could chuckle. Exactly. It's the ultimate cosmic plumbing system, that kind of playful metaphor helps make the abstract concept stick in the audience's memory. But as with all thrilling possibilities, reality forces a dose of caution. Physicists warn that these bridges, if they exist, may not be traversable. They might exist only for particles, not for spaceships or people. They might be too small, too fleeting, or too unstable for us ever to use. Still, the fact that the equations even suggest such bizarre possibilities is enough to keep the scientific imagination alive. There's also a philosophical layer here. Wormholes represent the possibility that the universe is more interconnected than we can currently perceive. They suggest that what disappears in one place might reappear elsewhere, that boundaries are not absolute, and that the cosmos may have hidden pathways threading through its structure. Whether or not they're practical for travel, wormholes anchored by black and white holes remind us how incomplete our picture of reality still is. The dialogue can emphasize this balance of wonder and caution. The skeptic voice, so basically, wormholes are the universe's version of cheat codes, but probably unusable. The explainer, for now, yes. But remember, people once thought black holes were pure fantasy, too. Science has a way of surprising us. That exchange keeps the audience both grounded and hopeful. The best way to close this section is to transition from the geometry of wormholes to the deeper concept of time. Because if white holes are the reverse of black holes, they don't just flip direction in space, they flip direction in time. That's where the story gets even stranger. You might end with a line like, if black holes represent the universe's future endpoints, where matter and time collapse, white holes could represent the past, rewinding the cosmic film. And that brings us to the mind-bending idea of time reversal. Now, we arrive at perhaps the strangest twist of all, the idea that white holes can be thought of as time-reversed black holes. If black holes are all about inevitable collapse into the future, then white holes represent the exact opposite, inevitable explosion from the past. This isn't just a poetic metaphor, it's a genuine feature of Einstein's equations, physics. In many cases, doesn't distinguish between forward and backward in time. The laws work the same in both directions. That's why, mathematically, a white hole is simply a black hole with time reversed. In the dialogue, the curious voice could ask, time reversed? What does that even mean? The guide might respond, think of a video of a black hole devouring a star. Now play that video backward. Instead of matter falling in, you see it flying out. Instead of light vanishing into darkness, it bursts outward. That's essentially what a white hole is in the math of black hole in reverse. This visualization is simple, yet it captures the astonishing symmetry of the concept, of course. This time reversal raises deep questions. The skeptical voice could push, but time doesn't really work backward in our everyday world, does it? Broken glasses don't reassemble themselves, and smoke doesn't go back into the fire. And that's where the conversation takes a fascinating turn. The guide might explain, that's true in our macroscopic world. Because of the second law of thermodynamics, entropy disorder always increases with time. That's why we experience a clear arrow of time, but the fundamental laws of physics don't actually care which direction time flows at the deepest level. They work the same going forward or backward. That explanation allows you to pull the audience deeper into the paradox. If the fundamental laws allow time reversal, why don't we see it? Why doesn't the universe behave symmetrically in that way? That's where white holes become so intriguing. They represent an allowed but unseen possibility, a kind of mirror universe where the arrow of time points outward instead of inward. The dialogue might dramatize it further. Speaker 1, so a black hole is like the ultimate future everything, collapsing into one point. A white hole would be like the ultimate past everything bursting outward from one point. Speaker 2, exactly. Some physicists even suggest that the Big Bang itself might be thought of as a white hole, an explosion of matter and energy that nothing could enter, only escape from. That line doesn't just tease what's coming next, the Big Bang theory, but also keeps the tension high. The idea of time reversal also resonates with human imagination. People often dream of time travel, of undoing mistakes or revisiting the past. White holes embody that fantasy in a way, not as literal time machines, but as symbols of reverse causality. They remind us that the universe is not bound to our limited, one-way perception of time. Of course, the skeptic voice can add humor here. So what you're saying is, if I fall into a black hole, I could pop out of a white hole in reverse time. Maybe even meeting myself as a baby. The guide could laugh. Not quite. The math is tricky. It's not that you'd rewind your personal timeline, it's that the object itself behaves as though time were flipped, but I like your imagination. Exchanges like this keep the audience entertained while still anchoring them in the science. There's also an important point to highlight about why we don't see time reverse phenomena in daily life. That comes back to entropy. Black holes are consistent with increasing entropy. They absorb matter, radiation, and information, creating more disorder in the process. White holes, on the other hand, would seem to decrease entropy by ejecting ordered material from nowhere. That violates what we observe about the universe, which might explain why we've never found one. Still, this doesn't erase them from the equations. They exist in theory, even if reality chooses not to play by that particular version of the rules. This is where you can get philosophical. One voice can say, maybe the reason white holes remain invisible is because they belong to a universe where time runs differently, a universe we're not part of. The other could respond, or maybe they only existed at the beginning of time itself, when the universe was young and the rules weren't as strict as they are today. These lines don't offer definitive answers, but they give the audience that sense of cosmic mystery that keeps them hooked. The beauty of presenting white holes as time-reverse black holes is that it makes the concept accessible without watering it down. Everyone understands playing a video backward. Everyone has experienced the one-way nature of time. By showing how white holes fit into that framework, you not only explain the physics, but also connect it to everyday intuition. To close this section, you'll want a line that bridges smoothly to the next part of the story. What roles white holes might actually play in the cosmos? A strong closing might be, so if black holes represent collapse and endings, white holes embody reversals and beginnings. And that leads to the biggest question of all. Could white holes actually be shaping the universe around us, hiding behind the unexplained phenomena we observe? Now that we've seen white holes as the time-reverse siblings of black holes, it's natural to ask, do they actually matter to our universe? Or are they just mathematical curiosities? This is where the dialogue can shift into speculation about the possible roles white holes might play in the cosmos, and here, the imagination can really run wild while still staying tethered to scientific ideas. Picture the scene. One voice asks with curiosity, if white holes exist, are they just sitting out there somewhere, spitting stuff into space? The other replies, that's one possibility. Some scientists think white holes could act like cosmic fountains, constantly pouring out matter and radiation into the universe, but because nothing can enter them, they would be incredibly difficult to detect. They wouldn't have the same telltale signs as black holes, like the hot disks of gas swirling around them. This sets up the tension, something that could exist yet remains practically invisible. One of the more adventurous theories is that white holes might be connected to black holes, possibly even as to ends of the same object. Imagine falling into a black hole instead of being crushed at a singularity. your matter might somehow travel through a tunnel and emerge from a white hole elsewhere in the universe. This is where the concept of wormholes gets pulled into the discussion, a topic that excites science fiction fans and serious physicists alike. The guide voice might say, it's like the black hole is an entrance and the white hole is the exit. Together, they could form a wormhole, a shortcut through space and time. The skeptic voice could counter, that sounds awesome, but if that were true, wouldn't we have spotted one already? Wouldn't there be strange streams of matter just appearing in the sky? The response could be, exactly, that's one of the problems. We haven't seen such things, and most physicists think wormholes, if they exist, would collapse quickly for anything to pass through. Still, the math doesn't forbid them, and that's why the idea lingers. Another possible role for white holes is in the early history of the universe. Some theories suggest they may have existed just after the Big Bang, or perhaps even were the Big Bang itself. After all, what is the Big Bang if not the ultimate white hole, an event where matter and energy exploded outward with nothing entering from the outside? The dialogue could build suspense here when you think about it. The Big Bang is like the mother of all white holes. Everything we see, every star, every planet, every atom came from that one eruption. That way, the audience feels the scale of the idea, connecting an abstract concept to the very existence of the cosmos. White holes might also explain certain cosmic mysteries, like gamma-ray burst, intensely powerful explosions that astronomers observe in distant galaxies. These bursts are so energetic that they defy easy explanation. Could they be brief appearances of white holes, spitting out energy before vanishing? That idea has been floated by some scientists, though it remains speculative. Including it in the dialogue adds a sense of immediacy, because gamma-ray bursts are real, observed phenomena that people can look up. Then there's the idea of white holes contributing to the mystery of dark matter and dark energy. While most scientists lean toward other explanations, a handful have suggested that white holes, if they exist, might produce effects that mimic these invisible forces shaping the universe. For example, white holes ejecting matter that quickly disperses could leave behind gravitational fingerprints without us seeing the source. This is fringe speculation, but it's the kind of what if that works perfectly in a YouTube dialogue, keeping the audience leaning and wanting to know more. The conversation could then shift slightly philosophical. One voice might ask, so, do white holes actually exist, or are they just mathematical ghosts? The answer could be carefully framed. We don't know. No one has ever observed one directly. But the fact that the equations of physics allow them means they can't be dismissed. They may turn out to be real players in the story of the cosmos, or they may just be symbols of possibilities, reminders that the universe might hold secrets stranger than anything we've yet imagined. The guide might then draw a metaphor. Think of white holes like mythical creatures in cosmology. They're like unicorns. No one's ever seen one, but the idea of them tells us something about how we imagine the universe. And unlike unicorns, white holes are at least consistent with the mathematics of Einstein's theory. The audience gets a smile from the metaphor, but also grasps the difference between science and fantasy. Finally, the section could end by building momentum toward the next big twist. If white holes might play roles in shaping the cosmos, then perhaps the most intriguing question of all is whether they could be connected to the ultimate mystery of time itself. The beginning of everything. Was the Big Bang a white hole? And if so, what does that make our universe? This tees up the next section in a way that leaves viewers eager to click next or keep watching. By focusing on roles, whether cosmic fountains, wormhole exits, gamma-ray burst sources, or even the Big Bang itself, this section makes white holes feel like more than abstract equations. It gives them narrative weight, inviting the audience to imagine how these unseen objects might be shaping their world. Right now, the question of whether white holes can be linked to the Big Bang is one of the most fascinating and daring ideas in modern cosmology. Imagine for a moment that everything we know, the stars, the galaxies, the atoms in our bodies didn't just appear from nothing in some incomprehensible explosion. Instead, what if the Big Bang was the ultimate white hole? A colossal outpouring of energy and matter, not fed by anything external, but instead emerging from the time-reverse twin of a black hole that existed somewhere or somewhen before our universe began. The dialogue here could open with one voice asking, what if the birth of our universe wasn't just a random bang? What if it was actually the eruption of a white hole? The other replies, that's exactly what some scientists have suggested. The Big Bang looks a lot like a white hole in disguised matter and energy spewing out everywhere, with nothing going in. This sets the stage for a truly mind-bending exploration. To grasp the connection, we can return to the core idea. Black holes and white holes are opposites. Black holes pull everything inward, white holes push everything outward. Now think about the beginning of the universe. At the Big Bang, space, time, energy, and matter all expanded outward from an infinitely dense state. No outside input, no pre-existing stuff being funneled, and it simply exploded outward. This is the very definition of a white hole's behavior. One of the more adventurous cosmological models suggests that perhaps our universe itself is the inside of a white hole. In other words, the event we call the Big Bang could be nothing more than the opening of a white hole into a higher dimensional space. This leads to a deliciously paradoxical thought. What if the collapse of a massive black hole in another universe or another region of space-time triggered the birth of ours? The voice in the dialogue might say, imagine some enormous black hole collapse somewhere else. Instead of ending in a singularity, It popped into existence as a white hole, and what came pouring out became our universe. That means our Big Bang might not have been the beginning of everything, but just the beginning of our chapter in a larger cosmic book. The skeptic voice could push back, but wait, if that's true, doesn't it just push the problem back one step? Where did the other universe come from? Where did the black hole that birthed our white hole universe come from? And here, the answer would be a shrug of cosmic humility. Yes, it doesn't solve everything, but it reframes the question. Instead of asking why there was something instead of nothing, we start asking what chain of black holes and white holes might create new universes endlessly, like cosmic dominoes. This idea ties into the concept of a multiverse, the possibility that there are countless universes, each potentially born from the white hole eruption of another. Our universe may not be the only one, it may just be one bubble in an infinite sea of bubbles, each expanding outward from its own white hole moment. The guide voice could describe this with a vivid image. Picture an endless ocean of soap bubbles. Each bubble is a universe. The moment each one pops into being is the birth of a white hole. And we, inside our bubble, mistake that moment for the Big Bang, never seeing the ocean beyond. But not everyone buys into this bold vision. Many scientists argue that the Big Bang is sufficiently explained by inflation theory, quantum fluctuations, and the dynamics of general relativity without invoking white holes. Yet, even they admit that the comparison is tantalizing. The Big Bang as a white hole helps ordinary people picture the unimaginable, an eruption of matter and energy without any apparent cause, a one-way explosion from nothing. To make the concept even more relatable, the dialogue could explore how this connects with the arrow of time in our universe. Time moves in one direction forward, entropy increases, stars burn out, things decay. But if the Big Bang was a white hole, then the arrow of time itself may have been set by that eruption. One voice might say, think about it, white holes are time-reversed black holes. If our universe came from a white hole, that would mean the very reason we experience time flowing forward is because of that initial outpouring of the Big Bang. That realization ties the grandest scales of the cosmos to the everyday ticking of the clock on your wrist. Of course, this line of thought comes with its dangers. It's easy to slip from scientific speculation into outright science fiction. So the dialogue should remind viewers, this is still just a hypothesis. We don't have proof that the Big Bang was a white hole, but the fact that the idea is even possible shows how mysterious the beginning of the universe really is. As the conversation nears its close, the host could reflect on the emotional weight of the question. If the Big Bang was a white hole, then our universe was born not in isolation, but as part of a larger cosmic story. We might be the children of another universe, connected through the strangest bridge imaginable, a white hole. That statement leaves the audience pondering not only the scientific mystery, but also the existential wonder of belonging to something larger. This section doesn't just speculate about cosmic mechanics, it connects the dots between the known, the Big Bang, and the unknown white holes, weaving them into a narrative that feels both scientifically grounded and philosophically profound. By the end, the audience feels the awe of possibility. Maybe our universe itself is the greatest white hole of them all. As we come to the final part of this journey, it's time to pull together all the threads, the science, the speculation, and the imagination, and reflect on what white holes really mean for us. Throughout this exploration, we've seen how white holes are not just quirky mathematical oddities, but profound thought experiments that challenge everything we think we know about the universe. They've been described as the cosmic siblings of black holes, theoretical portals that spew matter and energy rather than swallowing it, and even possible explanations for the most mysterious moment of all, the Big Bang. But after all this speculation, one pressing question remains: what do white holes teach us about our place in the cosmos? The dialogue might begin with one voice saying, we've spent so much time talking about what white holes might be, but maybe the real question is, what do they mean? And the other could answer, they mean possibility. They remind us that the universe is bigger, stranger, and more mysterious than anything we can fully grasp. White holes might exist, or they might not, but the fact that we can even imagine them shows how far human curiosity can reach for everyday people. The concept of a white hole stretches the imagination in the same way that black holes once did. There was a time when black holes themselves were dismissed as impossible fantasy mathematical curiosities with no real bearing on the physical world, and yet, today, we have photographed one. We have measured their ripples in space-time through gravitational waves. We have come to accept them as real. Who is to say the same might not happen with white holes in the future? The reflection here is that today's crazy idea may be tomorrow's breakthrough discovery. Another key takeaway is how white holes encourage us to think differently about time. In many ways, they are mirrors of our deepest assumptions. Black holes represent the inescapable pull of gravity, the collapse of order into singularity. White holes represent the opposite, the unstoppable expansion, the eruption of matter without source. By considering both, we begin to see that the universe may be governed by symmetries we barely understand. One voice could put it poetically: black holes are where things end. White holes are where things begin, and we, living between them, are caught in the river of time flowing from one to the other. This reflection also pushes us toward humility. Despite all our science, our telescopes, our equations, we still don't have a complete picture of reality. White holes might be real, or they might remain forever in the realm of theory. But the very act of entertaining the idea stretches our Understanding, it's like standing on a cliff at the edge of the known world, staring into fog, and realizing that there could be entire continents hidden just out of sight. We don't know if those continents exist, but we do know that the horizon is not the end. The dialogue might continue, you know. White holes are kind of like the universe's way of daring us to dream bigger. They say, don't stop at what you can see, imagine what might be beyond, and the response, exactly. Because even if we never prove that white holes exist, they still change the way we think. They remind us that physics isn't just about equations, it's about wonder. There's also an existential layer here. If white holes are connected to the birth of universes, then perhaps we are not living in a one-off cosmic event. Perhaps creation is ongoing, eternal, recursive. That thought can either be dizzying or comforting, depending on how you look at it. Some might find it terrifying, the idea that our universe is just one bubble among countless. Others might find it beautiful that we are part of an endless cycle of creation. A story that has no beginning and no end. Is the final reflection. The host might address the audience directly. White holes may never be proven. They may stay forever hidden in the math of relativity. But what they give us is more valuable than certainty. They give us curiosity. They push us to ask questions we might otherwise never dare to ask. And in the end, that's what science is, not just answers, but the courage to keep wondering. The conversation could then end on a note of wonder, leaving viewers with a lingering sense of awe. The universe began with a mystery, and maybe it will end with one too. In between, we're here, small beings trying to make sense of it all. And whether white holes exist or not, they remind us of one thing: the cosmos is vast, strange, and endlessly full of surprises. This final section serves as both a conclusion and a meditation. It ties together the science, the speculation, and the human response, leaving the audience not with closure, but with curiosity. Because in the realm of white holes, certainty is impossible, but imagination is limitless.